Yes, Helen, welcome. Today we are beginning on the effects of heat on substance, and we are looking at the effects that substances undergo when heat energy is provided. Uh, Looking at now, we begin on melting and boiling. What are the effects? What the changes that substances undergo when they are being melted or when they are being boiled? So changes in temperature can cause a substance to change its physical state. We say that physical states of matter, we have solid, liquid, and gas. So according to the provision of heat, the matter changes. The matter can change from either solid to liquid, from liquid to solid, and from solid to gas, and solid gas to liquid, or gas to solid. So a provision of heat makes matter to change from one state to another. So we are saying that water can be solid, that is in ice, liquid, that is water, and then gas, vapor or steam. So its state can be changed by heating or cooling. So the changing of the water, the changing of water from solid, which is now ice, can be changed through heating. Or now that is water, now liquid water can also be changed back to a solid, which is ice, now through cooling. So we'll be having an experiment to investigate what happens when ice is heated to boiling. So when ice is heated to boiling, now what changes it undergoes. So we have apparatus and chemicals we use. We have beaker, we have thermometer, tripod stand, wire gauge, Bunsen burner. So and then you have the ice cubes now that we'll be using. The procedure, we arrange the apparatus as shown. So we have ways on how we arrange the apparatus. So we place some ice cubes in a beaker. We place a thermometer in the beaker containing the ice cubes, and record the temperature. We record the temperature. We warm the beaker and its contents gently. So after having gone through the procedure, we'll have some observations that we'll make. We note and record the temperature at which the ice changes to liquid water. For we continue heating until water changes to vapor. Then record the temperature at which bubbles appear. So this is how the apparatus will be. We have the beaker. Inside the beaker we are placing in ice, then we are dipping in a thermometer inside the ice, and then the beaker and its content is placed on a tripod stand, and then we have a source of heat, that is a burner. So we explain the observation that we have. When ice is heated, its temperature rises steadily. Now as now we are providing heat energy, the ice is gaining the heat energy. Remember now, ice in the first case, it is solid. It's solid in its physical state. It is solid. Now it is gaining heat energy. This heat energy that it is gaining, it's using it now to break the forces holding the particles together. Using it to break the particles holding the ice together. So the temperatures are rising steadily. It rises steadily until all the ice melts. So the change is called melting. The change is called melting, and this temperature, and the temperature is the melting point. Now the temperature is melting point, and it is 0 degrees for pure water. It is 0 degrees for pure water. Now the entire of the ice melts at 0 degrees. So now remember, now the temperatures of ice are negative because it is too cold. So as the temperatures now are increasing, the solid ice begins to melt. So until all the ice has melted, it is when now the temperatures will begin to rise. So on further heating, the temperatures rises steadily and some of the water changes to water vapor. So remember now, after having reached 0 degrees, the entire ice now has changed to water, now in liquid form. Now it is liquid. Now water, in this case, it is liquid at 0 degrees. After the entire ice has melted, now it is 0. And then on further heating, you're saying that the temperature rises steadily and some of the water changes to water vapor. Now the water begins to gain more heat energy as the temperatures are rising. The temperature will rise up to 100 degrees. That is for pure water. After having reached 100 degrees, now the water will begin to change to vapor or steam. So this is called evaporation. Now it will start to evaporate. So the hotter the water gets, the quicker it evaporates, and soon bubbles appear. So the water is now boiling, and this is the boiling point. Now bubbles start to appear. When the bubble starts to appear, means that the boiling point of the water has been reached. So at sea level, the boiling point of pure water is 100 degrees Celsius. So we're saying that at sea level, the boiling point of pure water is 100 degrees Celsius. So the change of state from solid, that is ice, to liquid, that is water, and then from liquid to gas, vapor, can be reversed by cooling. Remember now, at initially we had ice, so ice has changed to water, then water now is finally changing to vapor. It's finally changing to vapor. Remember, in this case, we are increasing the temperatures. So solid ice, now it is gaining more heat, breaking the forces holding the particles in solid state, changing it to liquid state. Now it is water. Now in this case, the forces of attraction between the water particles, it's not that strong compared to the particles in the solid ice. So after the heat energy has broken the forces holding the water particles here, now it forms vapor or steam. So here we are increasing the temperature, and then now the reverse of it is, now we decrease the temperature. So we are saying it can be reversed by cooling. So on cooling, the gas changes into water. This process, we are calling it condensation. So we said from ice to liquid, we are calling it melting. From ice to liquid, from ice to water, it is melting. From water to water vapor, it is evaporation. We are calling it evaporation. Then from now, the water vapor or the steam to liquid water, we are calling it condensation. So we are saying on further cooling to below 0 degrees, the liquid changes into solid. The process called freezing. Then now from liquid back to solid, we are calling it freezing. Remember, as we are coming back from water vapor to ice, it is all about decreasing the temperatures. Now the temperatures are decreasing. So the freezing point of water is the same as the melting point of water, which is 0 degrees. So all these changes can be represented. Here. So we can see that from solid to liquid, it is melting and it is increasing temperature. From liquid to gas, it is evaporation or vaporization. It also entails increasing in temperatures. And then from gas back to liquid, it is condensation. Now in this case, we are decreasing the temperatures. Then from liquid to solid, it is freezing. This is now further decrease in temperature. So we are saying from solid to liquid to gas, it is increase in temperature. It is increase in temperature. Then from gas to liquid to solid, it is decrease in temperature. So now that's the an effect of heat on ice, an effect on heat on ice. So we are increasing temperatures, and these temperatures, they are causing the physical state of the initial ice we had to change. So we can conclude from the changes observed that something happens to cause changes in state of matter. The readings we note on the thermometer enable us to predict that the change in temperature must in a way be responsible for the determining the state of matter. Must be predict the change in temperature must in a way be responsible for determining the state of matter. But what determines whether a substance is a solid, liquid, or gas? So what determines the state, either a substance is solid, liquid, or gas? The explanation of the state in which it is likely to be is found under a given set of conditions known as kinetic theory of matter. So we will go ahead and look at this the kinetic theory of matter. So you say kinetics is from the Greek word which is kineo, which means I move. So kinetic matter is a Greek word. So kinetics is a Greek word. A Greek word, kineo, which means I move. So particles in a substance are in constant motion. They possess kinetic energy. So we looked at this, that particles in a substance are in constant motion. We looked at it by carrying out an experiment where we had particles of bromine that were placed in a gas jar, having at the back of our mind that bromine is heavier than air, then placed in one gas jar, then inverted by another gas jar. Then finally we came to observe that the entire of the two gas jars were filled with the red brown color of bromine, where the particle had been placed in a one gas jar, but the entire of the two gas jars were filled with the red brown color of bromine. So it means that the particles in substances are in constant motion. So as they were now moving, colliding with the particles of bromine, and then moving to other parts of the gas jars, colliding with the walls of the gas jars themselves, making them to be evenly distributed. Also another experiment that we carried out is that of the having some crystals of purple potassium manganate 7 that were placed at the bottom at the bottom of a beaker that had water, and after some time we came to see that the purple color was evenly distributed inside the water, throughout the water in the beaker. So this means that after having been left without being undisturbed, as the particles were colliding in the random motion, they collide, then making them to be evenly distributed. So particles in a substance are in a constant motion, so they possess kinetic energy or energy of movement. So they possess kinetic energy or energy of movement. So the theory explains how the particles are packed in solid, liquid, or gases. So the attractive forces between them and the effect of temperature on them. So kinetic theory explains that particles in a given substance, they are in random motion, and there are forces that hold them together. So in solid, the particles now are intact. So the space between the particles in a solid is less compared to that the space between particles in a liquid, and even the particles in a gas now, they have a larger space compared to that of those in liquids. So change of state in terms of kinetic theory. Let's look at the change of state in terms of kinetic theory. So we saw in an experiment that changes of state involve heat energy. Change of state involve heat energy. It involves heat energy. The energy is either being absorbed or given out. So as when we have ice, when we subject it to heat energy, so it absorbs the heat energy. Then the heat energy is used to break now the force of attraction between the particles of the ice. Remember now, in the ice, the particles making up the ice are held by forces together. So the heat energy is used to break the forces holding them together. So we are saying that changes of state involve heat energy either being absorbed or given out. So kinetic theory explains the changes of state of matter, the change of state of matter. So in kinetic theory, we will be explaining the changes of state of matter, So arrangement of particles in 3 states of matter, that is solid, liquid, and gas, are as follows. Like so in this image, you have just indicated on how they are arranged. So between the particles, you have intermolecular forces of attraction. So the forces are the ones that hold the particles together. So for that of the solid state, you will see that they have stronger intermolecular forces, because now the forces are bringing them more closer to each other as compared to that of liquid, and then more they are more weak in liquid state. So let's look at solid. So solids have strong forces of attraction between particles. So they have strong forces of attraction between particles. So particles are held in fixed position by the attractive forces. So when a solid is heated, the heat energy is gained by the particles. The extra energy makes the particles vibrate more and more. So as you are heating a solid, the heat energy is gained by the particles, and now this energy makes the particle to vibrate more and more, but within the same position. Further heating weakens the forces of attraction between the particles even more, and the solid changes to liquid. Now this is what we are calling melting. So that's the reason as to why when you are heating a substance, a solid substance, it will gain, the temperatures will continue rising. As now it is continue rising, that heat energy is used to break the force of attraction between the particles. So as the force of attraction between the particle is being as the substance is gaining more heat energy, now the particles continue to vibrate more and more. So as they continue vibrating, as the heat is continued to being supplied, now the forces are being weakened. Hence now another new physical state is formed. Now in this case, we are saying a liquid is formed. So the solid changes to liquid. So we are saying the change from solid to liquid is melting. Then looking at liquids have moderate force of attraction between the particles. So the force of attraction between liquids and solids, we can say that now the attraction between solids is more compared to that of liquid. So the particles are free to move randomly, but tend to stick together. Though they move, but they tend to stick together. So all liquids do not have definite shape and fill the bottom of any container. So that's what makes now the liquid not to have a definite shape, because now the particles are in motion, but they stick together, are in random motion but they stick together, compared to that of solid that now they are together. The forces holding them, they are strong, and now they are together. Then looking at the gas, so when supplying heat on the liquids, the heat energy is gained, and now this increases the random motion of the particles, hence making breaking the force holding together the particles, increasing the space where it makes it to move to change from liquid to gas. Now that is what we call evaporation or vaporization. Then looking at the gases, so when a liquid is heated, we are saying that the heat energy goes to the particles and make them move faster. So it increases the random motion. So the fast moving particles of the surface overcome the force of attraction from the other particles in the liquid, and escape into the air. So this is called evaporation. So the ones that have gained now the random motion, they'll escape to the air, and that is what we call evaporation. So you can see here that now here we have particles in a liquid move randomly but stick together, because now the distance is not that big. It's not that big. So as here now you have supplied the heat energy, it has been gained more and more. So some particles overcome the force of attraction and escape in the air. So as now they are escaping, those particles that now are escaping, they have overcome the force of attraction. Now the force of attraction between them, between that particle and the other particle, has been broken. Now it escapes. So that's the escaping, we are calling it evaporation. The escaping of the particles, we call it evaporation. So the above changes of state can be summarized. So we are summarizing the entire change of state as now this is the liquid state. You can see that now the particles are held together. Now the distance from one to another is not that big as compared to that of the liquid state. So the liquid state, you can see that the particles are somehow far from each other, but they have the force of attraction between them. So as we supply heat to the solid state through melting, it changes to liquid. Then as we continue providing heat to the liquid state, through gaining of heat energy, breaking of the forces now between the particles, the evaporation occurs now to form a gaseous state. So we say that when the liquids get hot enough, all the particles acquire enough energy and speed up to overcome the force of attraction between them, and most escape from each other to the air. That's why when we are heating when now we are boiling water, the entire water will not just evaporate at once, but now it will evaporate in turns. After each and every particle has gained more heat, more energy, they now after the particle has gained more energy, it has overcome the force of attraction. Each and every particle will leave at its time, not that they leave at once. So that's why it takes time for the entire of a liquid to evaporate. So during boiling, big bubbles of gas from inside the liquid as the particles break away from each other. So it is possible to compress gases easily because there is a lot of space between them. So you can see that the particles of a gas are far from each other as compared to those of liquid, and then so making it easier to be compressed. That's why you can see that in a cylinder of gas, there is a gas that has been compressed inside. You can see that just inside a cylinder gas, we have 6 kilograms of gas. 6 kilograms of gas particles are inside there. So the space between the gas particles makes it easy to be compressed easily, because there is a lot of free space between the particles, unlike in solid and liquids. Unlike solid and liquid. So liquid cannot be compressed. Liquid cannot be compressed, neither can solid be compressed. So condensation. So during condensation, the kinetic energy of the particles of a gas is decreased. So condensation, now we are saying that condensation, we are now reducing during the condensation, the kinetic energy of the particles of gas is decreased. So condensation, now we have a gas that now it is turning to a liquid. It's decreased. The particles come closer together, and the forces of attraction between them increase. Then a liquid is formed. So this process, we are calling it condensation. The process is condensation. Then you have freezing, that involves the kinetic energy of a liquid particles even that involves decreasing the kinetic energy of liquid particles even more. So the particles come even closer together, and the forces of attraction between them increase, so that they only vibrate within the same positions. So a solid is formed, and the process now we are calling it freezing. So we have permanent and non-permanent changes. So we say that heat, permanent and non-permanent changes, mostly we have heat energy that is involved. So heat causes many substances to change. So we can remember what happened to ice when now we subjected it to heat. When you subjected it to heat, so ice and water, when they were heated or they were subjected to heat, so what happened when these substances were cooled? So as provision of heat, and even if they are cooled, there are changes that occur. So we learn more about the effect of heat on substance in this section. So in this section, we are learning more about the effect of heat on substances. So heat can be dangerous, even fatal if mishandled, not just in the laboratory but at home as well. So we have to handle heat with a lot of care, because if it is mishandled, it can be fatal and dangerous. It's not only in laboratory but also also as well as at home. So always we exercise caution when we are using heat. In chemistry, observations are made on experiments. Saying that in chemistry, experiments are made. In chemistry, observations are made on experiments that involve heating substances. Observations are made on experiments involving heating substances. So in this section gives some guidelines to follow when now heating substances in the laboratory. In addition, always follow the instruction given for specific experiment. So in addition of the guidelines that now we are going to look at, we also have specific instruction given for experiment. So safe rules to remember when heating substances: 1. Ensure that the test tube or the boiling tube is dry before use. Ensure that the test tube or the boiling tube is dry before use. 2. Make use of the test tube to heat solids. So we make use of test tubes to heat solids, but boiling tubes are preferred when boiling liquid. Boiling tubes are preferred when boiling liquids or solution, and for large quantities of liquids or solution, beakers are preferred. Then we hold the test tube or the boiling tube with test tube holders. So boiling liquid or solution in boiling tubes or test tubes that are less than a fifth full. So the liquids in boiling tube or test tube have to be a fifth full, have to be less than a fifth full. While boiling liquids or solution, face the mouth of the test tube away from ourselves or our friends or even our books, just in case of spatting. Then we always heat gentle at first, holding the tube at an angle to the flame. Always heat gentle at first, holding the tube at an angle to the flame. Then from time to time, we move the tube away from the flame. If we have to smell any gas, we hold the tube some distance from the nose. Then using our hand, we waft some air above the tube towards our nose. So in case you want to smell the gas, we waft it. In this way, we can safely smell any gas that might be given off. So when heating solids, we look for changes in color or the color of the gas being produced. We also listen out for the sound too. Also, we look for water droplets, condensing and sublimation on the cooler part of the tube. If necessary, we heat strongly. And repeat the observation for smell and other evidence for change. We note the change when the residue cools. So changes, we can note them when the residue cools. Always use a small and luminous flame so that blackening of the glass does not occur, where blackening of the tube makes it difficult for us to make accurate observations. So as we had said that the amount of liquid has to be less than a fifth itself, or less than a fifth. So let's look at non-permanent changes. Where we have an experiment to determine the effect of heat on some substances. So apparatus and the chemicals required have a test tube, Bunsen burner, test tube holder. Now the chemicals that we are using have wax. Remember, now it's not a one experiment, but a number of experiments. So you have wax, you have ice, you have sulfur powder, you have zinc oxide, you have lead oxide, iodine crystals, ammonium chloride, and then sodium chloride. So the procedure, we begin now with wax. We place pieces of candle wax in a test tube. We hold the test tube with the test tube holder and heat, and then allow it to cool. So we repeat the experiment with the small quantities of the other substances too. So we are saying we use a clean dry test tube in each case. So these are the observations that we make from those experiments. That when we carry out, this is what we will observe. So while using wax, we'll realize that on heating it melts to form a liquid wax, and then on cooling it solidifies to form the solid wax again. So in this case, there is no change. There is only a change in the physical state, where now it turns from a solid to a liquid. But as the temperatures now are reduced, because we had increased the temperature by provision of the heat energy, as the temperatures now as it cools, now it forms the initial solid that we had of wax. Then on using iodine forms a purple gas when heated. Then on cooling, the gas forms solid iodine again. So we refer to such change as sublimation. Remember, we said sublimation, now the solid is changing directly from solid to liquid. and liquid from solid to gas, and again from gas to solid. So we are saying on heating the solid changes to gas, and then on cooling the gas changes to solid directly. So we are calling that sublimation. Then on using zinc oxide is a white solid when cold. So when heated it does not melt but just turns yellow. So when heating zinc oxide, it also turns there is only a change in the color. So a white solid when cold, and when heated it turns to yellow. So on cooling it turns to the original white colored substance that we had before. So zinc oxide is white when cold and yellow when hot. So it only experiences color change. So in the above experiments, the changes which took place are reversible. So as you have seen, the changes can be reversed back to the original substance. So this means that the original substance was obtained upon cooling. None of the substance heated formed a new substance. So changes like melting, boiling, evaporation, and sublimation are reversible. So they are called non-permanent changes or physical changes, because we will only experience physical changes. So they are non-permanent changes. We know that zinc oxide changed only in color. It changed in color only. It also therefore underwent a physical change, because zinc oxide is white when cold and yellow when hot. So let's now look at permanent changes. So at that we have been looking at non-permanent changes. So to investigate the effect of heat on some substances, so the apparatus and the chemicals that we are using in this, we have a test tubes, we have Bunsen burner, we have test tube holder, we have a thermometer. The chemicals that we are using, we have copper 2 sulfate crystals, potassium manganate 7, we have copper 2 sulfate crystals and potassium manganate 7, copper 2 sulfate crystals and potassium manganate 7 So now we have the procedure. We have placed some small crystals of copper. Now we begin. Remember, now we are in this, we are carrying out two different experiments. So now we begin with copper 2 sulfate. So we place some small crystals of copper 2 sulfate in a dry test tube, and if the crystals are wet, we dry them with a blotting paper. So we note the color of the crystals. So we heat copper 2 sulfate until there is no further change. Then we remove the delivery tube. So remember, as we are now setting up the apparatus, after heating, after you have noticed that there is no further change, we first remove the delivery tube while still heating, so that to prevent sucking back of the liquid that you have obtained. So then we remove the delivery tube. While still heating, otherwise the collected liquid will be sucked into the cooling tube. So we remove the delivery tube while we are still heating, so that to prevent sucking back of the liquid into the cooling tube. So we allow the test tube to cool and divide the solid into two portions. Then we divide the solid into two portions. Now this is how the apparatus will be. So we are saying that this delivery tube, we remove it we remove it while still heating, so that to prevent this so liquid that you have obtained from being sucked back into the cooling glass, into the cooling or into the cooling tube, So we label the test tube containing, so remember we say that we are now dividing the residue into two, and then we label the tube containing the collected liquid as A. We measure and record the temperature of the liquid, then we put an equal amount of water. The equal amount should be equal to the liquid inside the liquid now that we have collected and indicated as A. We put an equal amount of water in another test tube and label it B. Then we measure the temperature of the water and record it. We add the first portion of the residue into the liquid in the test tube A and record the temperature changes, and then we add the second portion into test tube B containing the water, and also we record the temperature. We also record the temperature change. So remember that we are now having two test tubes, that of the collected liquid and then another of the water. So when copper 2 sulfate crystals are heated, the colorless liquid given out is water. So we cannot just say that it is water from just the appearance, but now we have to test to ascertain that it is water. So how do we test it? So when it is added to anhydrous, to white anhydrous copper 2 sulfate, the copper 2 sulfate turns blue. The white anhydrous copper 2 sulfate turns to blue. So hydrated copper 2 sulfate that is blue in color, when now we provide heat, it forms anhydrous copper 2 sulfate that is white in color plus water. So copper 2 sulfate crystals are also known as hydrated copper 2 sulfate. It's also known as hydrated copper 2 sulfate because now the water is what makes them to be in crystals. So we note that there are we note that we are using heat energy to drive out the molecules of the water from the crystals. Then now the water that we are getting is what we are calling the water of crystallization. So this water is known as the water of crystallization. So it is the one that gives the crystals a blue color. Without water of crystallization, copper 2 sulfate is a white powder. Copper 2 sulfate is a white powder. So copper 2 sulfate is a white powder, but on addition of water, it becomes blue in color and now in crystals. It is said to be anhydrous copper 2 sulfate. It is said to be anhydrous copper 2 sulfate. When we add water to the anhydrous copper 2 sulfate, it turns blue and becomes hydrated. The reaction that takes place is as follows. Now we have anhydrous copper 2 sulfate that is white in color, and then on addition of water, it is hydrated copper 2 sulfate and in blue in color. So this is an example of a reversible chemical change. And if we keep anhydrous copper 2 sulfate in a moisture-free place, it will remain white. So it remains white because there is no water. So we can write the above reaction as follows. So we have hydrated copper 2 sulfate. On provision of heat to it, there is removal of water to form anhydrous copper 2 sulfate plus water. And then when we add water to the anhydrous copper 2 sulfate, the hydrated copper 2 sulfate is formed. So we have two arrows, meaning that the reaction is reversible. So there are other reversible chemical changes that we will study, or we will look at them later. So in the second experiment, where we had potassium manganate 7, in the second experiment we had potassium manganate 7, so the apparatus and chemicals. So we have a Bunsen burner, we have a test tube, we have a trough, we have a splint, we have potassium manganate 7 itself. So procedure: we use the end of a spatula to put 2 portions of potassium manganate 7 in a hard glass test tube. Then we note the color of potassium manganate 7. So potassium manganate 7 is purple in color. We heat and collect the gas X. So the gas that we'll be collecting, we name it as gas X because we don't know which gas it is. But after the experiment, after the testing of the gas, we will know which gas it is. So we test the gas collected with a glowing splint. We observe the color of the residue and fill the table. Observe the color of the residue. Now this is how the apparatus, this is the setup of the apparatus. So here we have potassium manganate 7. Now we are providing heat to it so that decomposition takes place, and there is a gas production that now it's being collected over water. Potassium manganate 7 is purple. On heating, a black residue is produced, or a black residue is formed, producing gas X, which relights a glowing splint. So a glowing splint is rekindled with oxygen gas. So now a gas that relights a glowing splint, that is an oxygen gas. So therefore gas X is oxygen. So potassium manganate 7 was decomposed by heat to produce substances. We have potassium manganate, we have manganese oxide, and oxygen. So those are the products of the decomposition of potassium manganate 7: potassium manganate, manganese oxide, and oxygen. The reaction can be represented by the following word equation. We have potassium manganate 7 being decomposed to form potassium manganate, oxygen, and manganese oxide. So it is not possible to add oxygen to potassium manganate to get back potassium manganate 7. Therefore the change which has taken place in this reaction is permanent, or it is irreversible. So in other words, it is a chemical change. In chemical changes, new substances are formed. So in this case, we have formed a new substance. New substances have been formed, where when the new substance are reacted, the initial substance we had cannot be formed. So you have differences between physical and chemical changes. So physical changes and chemical changes. In physical change, there is no new substance formed, while in chemical change, there is a new substance that is formed. So no energy is either given out or absorbed in a physical change, while in a chemical change, there is an energy. Energy is usually given out or absorbed. So it is either chemical change or permanent change. While a physical change, it is physical change or non-permanent change. So the third difference, that the mass of the substance does not change. The mass of the substance does not change. while in the chemical change, the mass of the substance changes. So the change is usually reversible in physical change. The change is usually reversible in physical change, while in chemical change, the change is usually irreversible, but with some exception. However, there are some exception to differences. So in number 2, we say that no energy is either given out or absorbed. So we have some exceptions. For example, there are some chemical reactions which are reversible. We have some chemical reactions that are reversible. So example, we have calcium carbonate. When we heat in the decomposition of calcium carbonate, we'll have calcium oxide and carbon 4 oxide as the product. So this reaction can be reversed as follows, where calcium oxide being reacted with carbon 4 oxide will have calcium carbonate. So that's an exemption there's an exemption for a chemical change that is reversible. So we have a number of exemptions. So we also have ammonium chloride. When in decomposition of ammonium chloride, we have ammonia and hydrogen chloride. When we react ammonia and hydrogen chloride, we will have ammonium chloride, and then more of it will be learned later. We'll learn more about reversible chemical changes later. So remember to subscribe, like, and comment, not forgetting to share.